Okay, so let us consider this first example here. We have a 3-hinge arc here. We have the bars that is carrying this horizontal member here, and along that horizontal member there is a 500 pounds per foot loading. So as we can see here, we need to determine the loading at point D, so that we are going to show that the arc is subjected only to axial compression at any intermediate point like point D. So basically we are going to have the idealized structure for this first, and we note that in every length here, since this is a spandrel, we can use the equation of the parabola. We can also use this spandrel as a basis, or this largest spandrel here, and just proportion it to the smaller one, and that is the smaller one. That is why this equation was derived here. So how was that? We'll just have to ratio the y is to the y of the smaller spandrel, and the x is to x of the larger to the smaller spandrel. So we used y first, that is 25. Okay, and then proportion it to the square of the x, which is 50. And y is 50 because x here is bending, and it is actually bending downwards. That is why it is indicated. We have indicated negative here. So we have to indicate it by a negative sign. And then this will be further equated to the smaller spandrel. So if this small dimension here is y, and this is x, we can say that y is to x squared. So by cross multiplication, solving for y, we have this equation. Actually, this is the equation here. So moving on, we are going to have the idealized structure here, naming our A, B, and C points. So first, we are going to consider the whole structure in order to come up with AY and CY. And it is just sharing the symmetrical load here. And this 500 pound per feet can be resolved into its resultant here, that is 500 times 100, and that is actually 50,000 or 50k or 50 kips, because 1,000 kips or 1,000 pounds is 1 kip. So this is 50,000 pounds actually. So by that we can employ summation moments at both supports in order to determine AY and CY. However, AY and CY will just have the shared. We'll just have to share 50,000 here. So therefore, both will have a 25,000 pounds reaction. So AX and CX will be determined by separation. So if this is the separation considering the right portion, there will be BX and BY here, and CY and CX. We just write CY here, 25, and of course, this was already bisected the distributed load. So if this is 50 pounds per feet, just multiply that by the distance 50. So 25 times 50, or sorry, 500 times 50 is actually 25k. So in order to determine CX here, we now take moments at B. So we have first 25k times 25. Then the CY, negative rotation, 25k times 50. And then plus CX, a clockwise moment, times 25 is equal to 0. So we can now solve CX to be also equal to 25k. Okay, by summation forces horizontal, we can just say that BX is also CX, and that is actually 25 kips or 25,000 pounds. So knowing all of the reaction, so let us have to consider here point D. Okay, so this is point D. Okay, and then we need to illustrate a section at D. And at that section, we can obtain this. Okay, so we have a section here or a cut section from this D. And if this is the cut section AA here on the left portion, we need to indicate a force horizontal here. Say this member here, but this member shall carry no loading because this horizontal pin here is carried by your arc here. So we indicate a zero force member on that horizontal member here. So if we are going to determine all of the force transmitted on the bended member here, we need to indicate the shear that is perpendicular to the member, this one, and the normal force that is parallel to the member at point D. Say that is the parallel member. And of course, there will be a bending moment at point D. And so the bending moment could be derived by the three equilibrium equations as well as the VD and the normal at D. So VD is the shear at D and D is the normal at D at this particular point here. So at that particular point, we need to know the slope so that we can work on the components. Okay, so in this figure, it was already indicated, or the angle was already indicated, and where this angle came from. So this angle actually came from your slope D. And recall that our equation is this one. Y is equal to negative 25x squared all over 50 squared. I'll just bring it in here. So why do we need to have the y equation? Because y equation could be derived so that we can have the slope. Because remember that the differential of y with respect to x is actually the slope or the tangent theta. That is why this is rise all over run, or vertical all over horizontal, or the difference is actually the slope, which is equal to tangent theta. So we derived y with respect to x, and that becomes dy over dx. We copy the constant and then derive x squared, and the derivation of x squared is actually 2x. And further, if we are going to have to simplify this, 25 times 2 is negative 50 all over 50 squared, is we have a result of this one. Okay, so one of which will cancel, so that your dy over dx becomes 1 over 50x. So where is d located from your x? Okay, so d is located from your x actually 25 feet from C. Okay, so actually that is your reference. Okay, we just say here that when x is 25, we have 25 over 50, which is equal to negative 0.5. So we retain the negative there. Anyway, negative just simply indicates that your slope is decreasing. Okay, so with that, remember that dy over dx is actually tangent theta. And your tangent theta will be equated to negative 0.5, so we can get the angle. So that angle will be equal to 26.57 degrees. That is why this indicated here the angle, 26.6 degrees. And it is actually referred to the horizontal line. So we can see that your normal is inclined at the horizontal line. Okay, remember this. that if you have an angle here and then draw a perpendicular to this angle, okay, so this is perpendicular combined with the vertical, then this will be also the angle. So same true with this. So your normal at D is 26.6 degrees, and then remember that VD, or the shear at D, is actually perpendicular to your point D here, so that combining with the vertical line, this is also 26.6 degrees. So angle is very important to determine the component here, so that we can actually work with the unknowns. So working with the unknowns, we'll just have to apply the three equilibrium equation and the moment for the moment at D. However, where 6.25 came from here, we'll just have to go back to the y equation. So this is the y equation, okay? And then what is your x, where your height is unknown. So say this is y, our y, or let us label this as our y, okay? So label that as our y, and then this is our y, being proportion to the larger spandrel a while ago, and your x is 25, okay? So we'll just gonna use this equation. So when x is this one, that is 25, we'll just try to substitute it in this function. So therefore, calculating that one, we will have actually 6.25. So why do we need to have 6.25? So that if we're going to take moments at D, then we can compute for the value of the moment at D. So let me just highlight that one. So first, we are going to summation forces along X is equal to 0. So first we have rightwards 25, and then normal at D is actually leftwards, and it is adjacent to your reference angle 26.6 degrees. So we're going to use cosine function. So I'll just move it a little left here, and then your shear at D would be towards leftwards also, but your component, horizontal component, is opposite your reference angle. So that is using sine function is equal to 26.6 degrees. So we have ND, VD towards left, and 25K towards right. So we can equate it to 0. So we also simplify this. Let us transfer your constant on the right side, or just these two on the right side. We have this equation. So I'll just delete this and then say this is equation 1, to be supplemented by another equation formed by this vertical summation. So on the vertical summation, starting with the normal at D, so where's the normal at D? So here it is. Normal at D on the vertical will be towards upwards, and the component is opposite the angle 26.6 degrees. And then for VD here is going downwards with the component adjacent to the reference angle. So we're going to use cosine 26.6 degrees here as a multiplier, and then this distributed load here, okay? So the distributed load is 500 times 50. Okay, so this is actually 500 times 50, or we should say 25. So this is 25, okay? 500 times 25 is 12,500 pounds or 12.5 kips. Okay, so this is the result, 12.5 kips, and that is towards down. Okay, so equate this to 0. So we again simplify, bring your constant to the right side, then we'll have this second equation. So we have two equations with two unknowns, the same arrangement, where constant at the right side, we'll just have to calculate the value of ND and VD, or the normal at D and the shear at D. And we will be having this result. So actually, if we are going to stick with the angle a while ago, that is 26.57, ND will be rounded to 28 and VD will be almost equal to 0. So as we have the result, we have just proven that we have an almost equal to 0 shear here. So actually this could be rounded to 0 because this cosine 26.6 here was just rounded to this number, and actually the original value is 26.57. So anyway, these are the results, and then now we are going to take moments at D in order to solve the couple at D. So doing that, we have summation moments at D is equal to 0. So at this point, we consider here 12.5 times 12.5 feet, and that is actually a negative rotation plus this one, 25 kips times 6.25. So this will be equal, we deduct MD or the couple at D and equate it to 0. And actually we will end up with a value equal to 0. So that is why you have just proven that your shear here is negligible, as well as the moment will be equal to 0. So in most cases, your bended member here will be tend to have a normal force, or that is an actual force actually. So ND is the normal force at the slope D. So that is for this problem. Let us try another one.